Okay, any questions up to this point? Now, from now on, I will be just looking at some calculation of the vector potential. Let's look at the vector potential. And let's start with an example. Let's take a ring, again, just a ring, the problem that we had already solved. A ring on the xy plane, which carries a current I. We already know that the vector potential, we can write it in the form J of r prime divided by r minus r prime 1 over c. This is the vector potential at the point r. Okay, one problem. Does this satisfy the Coulomb gauge? Is this the vector potential we have for the Coulomb gauge? So we already said that I can obtain this vector potential in the Coulomb gauge, but I didn't check that it actually satisfies my Coulomb gauge. So let's see why it satisfies the Coulomb gauge. Divergence of A. This will be equal to 1 over c. This is dv prime, j of r prime, let me write it in this form, the divergence of j of r prime divided by r minus r prime. But this will be equal to 1 over c times dv prime times j of r prime, scalar product with the gradient of 1 over r minus r prime. Because that gradient only acts on the r coordinate, not the r prime coordinate. Which will be equal to 1 over c times dv prime j of r prime minus the gradient with respect to the r prime coordinate of 1 over r minus r prime. Since it's a function of r minus r prime only, I can replace the gradient with respect to r with gradient with respect to r prime. I just need to add a minus sign. Now I can do an integration by parts. So the divergence of A will be equal to minus 1 over c dv prime. Gradient, let me just put the gradient prime, or the divergence prime of j of r prime divided by r minus r prime minus the divergence of j divided by r minus r prime. Now the first time is the volume integral of a divergence, which I can write as a surface integral. And the second one, the divergence of j is 0. Because you see, continuity equation tells me that del rho by del t plus the divergence of j should be equal to 0. This is the conservation of electric charge for any phenomena. In magnetostatics, del rho by del t is equal to 0. Nothing changes in time. So this basically tells me that the divergence of the current density should be 0 in any static problem. But this, so the second term is automatically 0 because the divergence of j is 0. Well, the first term is 0 because I'm integrating over all of space. So my area over here is the boundary of all of space, which is at infinity, but at infinity there is no current. So that at the surface of my volume, j is 0.
The same could be said about the other term.
This the divergence of j term, but I cannot convert it to a surface integral. it's not the divergence of, I mean, the integrand is not the divergence of an expression. It's the divergence of an expression divided by some other function. So if r minus r prime was not there, then I could say, but that second term is not the, as a whole, it's not the divergence of an expression. Only the first term is the divergence of an expression. So I can only convert the first term to a surface integral, not the second one. So you see, this is basically crucial to have the Coulomb gauge in this. This is crucial for the vector potential to satisfy the Coulomb, written in this form, to satisfy the Coulomb gauge. So let's come to the calculation of this, the vector potential for this problem. Now, of course, the first thing we have to do is what is J? What is the current density in this problem? Let me use the spherical coordinates to write the J vector. So what is J? It's in the phi hat direction. Let me also call the direction to be phi hat. Well, it is only on that when r is equal to capital R and okay, you prefer the cylindrical coordinates, fine. And multiplied with? Well, let's say A. I don't know. Well, let's not say A. Let's call it C. It will be I times, let's not also call it C, I times some coefficient D. Let's determine what this D is. Now let me integrate it over the YZ plane. Integrate J over the x is equal to 0 and y is larger than 0 half plane. So if I integrate over that plane, that is J r multiplied with the s, the direction is in the minus x hat direction, or let's say the x hat direction. Let me choose my surface area to be the x hat direction. So what should the result be? I or minus I? You see, this is my ds vector. ds vector is in the plus x direction. But on that plane, which is the x is equal to 0, but y is positive, so it is this region over here, that semi-infinite plane, the current is running in the minus I direction. So the minus x direction, sorry, which is in the opposite direction. So this is minus I. So on this plane, phi hat is also minus x hat. So minus I should be equal to phi hat minus z hat, well, minus x hat, and x hat just gives me minus 1 minus I times d times Dirac delta r minus the capital R ds. Well, he preferred to use cylindrical coordinates, so i's I can just cancel. 1 is equal to d times the integral in cylindrical coordinates, this area element I can always write as dr, dz. Do you agree? So I take this very small area over there. This is my dz, and this is my dr. Do you agree? Times the Dirac delta of r minus r. Okay, z goes from minus infinity to infinity, dr goes from 0 to infinity, and this will be equal to d. So d is 1. So we know that j is equal to Dirac delta r minus r Dirac delta z times I in the phi hat direction. Do you agree? So J, no, sorry, A, the vector potential at the point R will be equal to 1 over C Dirac delta R minus R Dirac delta Z I phi hat cross R minus R prime, this phi hat at the point R prime. Cross R minus R prime over R minus R prime cube. And then I integrate over dv prime. Let me write it in cylindrical coordinates. This is, this is R prime, this is Z prime. So this will be equal to the volume element in cylindrical coordinates is dz, r dr d phi. Of course, all of these are the prime coordinates. R is my observation point. So z goes from minus infinity to infinity. R prime goes from 0 to infinity. Phi prime goes from 0 to 2 pi. Dirac delta of R prime minus R, Dirac delta of Z prime, I phi at the point R prime cross R minus R prime divided by R minus R prime magnitude cube. Now I can evaluate two of the integrals, which will just give me I over C. Well, the Z prime integral, I can just evaluate the Z prime and the R prime integrals, and I'm left with the phi prime from 0 to 2 pi of phi hat at the point R prime, whatever R prime point I will use, cross R minus R prime over R minus R prime cube. Of course, now this point R prime has the R coordinate, the radial coordinate equal to capital R and the Z coordinate equal to 0. So this is A. Well, this is not a great surprise, by the way. Just look at this expression. This is nothing but 1 over C R d phi prime times in the phi hat direction times I cross R minus R prime over r minus r prime cube. But you see, this thing over here is nothing but r dl. So this expression is actually, the vector potential is I dl cross r minus, oh sorry, what did I do? It's not r minus r prime over r minus I prime cube. It's just 1 over r minus r prime. I'm not writing the b, I'm just writing a. I don't have cross products in the definition of a. It's I dl over r minus r prime. So this is what we have. Now, so you see, this is my point r prime. I'm looking at the vector potential over here. This is r. Just for, I have this rotational symmetry in my problem. So if I just rotate my system, nothing should change. Okay. So I can basically calculate the my vector potential at a, let's say on the yz plane, at an arbitrary point on the yz plane. The rest I can just obtain by rotation. Do you agree? Well, that's what I will do. I will just choose R to be on the yz plane. Y larger than 0. For an arbitrary point, I can just obtain it by rotation. So let's write these components first. I have phi. Well, let's just start with writing this r minus r prime vector magnitude. What's the magnitude? Now r prime, I can just write it as, let's see, r prime in the r hat direction, r hat prime direction, let's say. Okay, so let me use Cartesian coordinates for the calculation. It will be kind of easier for me. In Cartesian coordinates, this will be the length of r vector is, well, the x component of the r vector is 0. Y component of the r vector is just r. Remember, r is not the radial component, it's not the distance from the origin, but it's the distance from the z-axis. That r point is on the yz plane, so the y coordinate is already r. And the z component is z. Minus, well, this r prime vector, this angle is what we call the phi angle. So r prime vector has the x component r prime sine phi in the x direction plus r prime cosine phi in the y direction. So this length is r prime sine phi, r prime squared, sine squared phi, plus r minus r prime cosine phi squared, right? Plus z squared under the square root. And phi is phi prime. This is equal to r prime squared sine squared phi plus r squared minus 2r r prime cosine phi prime plus r prime squared cosine squared phi prime plus z squared which is equal to r prime squared. I have sine squared phi prime and cosine squared phi prime. The sum is just 1. So that's r prime squared plus r squared minus twice r prime cosine phi prime plus z squared to the power 1 over 2. Well, the thing that will be interesting for me, the thing that I will be using, is that this is symmetric if you just change phi to phi prime. You see, at this point, phi hat at the point r prime will be this vector over here, which will be a minus sine phi in the phi hat direction plus cosine phi, no, minus sine phi in the x hat direction plus cosine phi in the y hat direction, phi prime. This is my phi hat vector. So let's just put it in the expression of our vector potential. This is my vector potential. And this is my phi. And r minus r prime is this one. The A r will be equal to I over C r integral. But instead of integrating from 0 to 2 pi, I can also integrate it from minus pi to pi. It will make certain things more clear. D phi prime. So I have minus sine phi prime x hat plus cosine phi prime in the y hat divided by r prime squared plus r squared minus 2r r prime cosine phi prime plus z squared under the square root. You see, there I have the first term in the x hat direction, which is an odd function of phi. You see, the numerator is an even function of phi, in phi prime. Sine phi prime is an odd function. If you multiply an odd function with an even function, you get an odd function in phi prime. You have an odd function integrated over an even interval, but that gives you 0. So the first term is just 0. So A of r is equal to I over C times r integral from minus pi to pi of d phi prime cosine phi prime divided by r prime squared plus r squared minus 2r r prime cosine phi prime plus z squared to the power 1/2, and this is in the y hat direction. This is true if r is in the yz plane, y larger than 0. So A only has on the yz plane. Well, this basically tells me that on the yz plane, you see, it's in the y hat direction, the A. Did I make a sign mistake over here? No. Now I can generalize it. You see, for an arbitrary point, the A of R would be equal to I over C multiplied by R from minus pi to pi of d phi prime cosine phi prime divided by R prime squared plus R, this factor. You see, y hat vector, let's go back over here. Now, y hat vector is just this vector over here. Now, as I'm rotating my system, y hat vector should also rotate. Y hat vector is nothing but the r hat vector. Now, if you have the r hat vector on the yz plane, it just becomes the y hat vector. So here, this is in the r hat direction. Well, of course, then you need to try to evaluate or approximate this integral over there. Well, let's do one thing. I mean, if you remember from the electrostatic case, we have this dipole approximation. We are very far away from our current. So that is, let's assume, and by the way, this r prime is nothing but the capital R. Remember, r prime is the distance of this point from the center, but that is what we call the capital R. So let's assume R is much, much larger than capital R. Or let's say R squared. R is much larger, or Z is much larger than capital R. Or since we already, let's just keep Z and R, they are both much larger than capital R. Or let's see, we already have one solution, okay, along the Z-axis. We know the magnetic field. So we can try to calculate that magnetic field. So along the Z-axis, basically it's the Z that is the largest one. Z is much, much larger than capital R and small r. We are somewhere along the Z-axis, but far from our dipole. Now in this case, we have 1 over r squared plus small r squared minus twice r capital R cosine phi prime plus z squared to the 1/2. This is equal to 1 over z, 1 over 1 plus x to the power 1/2, where I defined x to be r squared plus small r squared minus twice capital R small r cosine phi prime divided by z squared. So this is approximately 1 over z, 1 minus x. So which is 1 over that thing to the power minus 1 over 2. This is 1 over z, 1 minus 1 over 2, and r squared plus small r squared minus twice capital R small r cosine phi prime divided by z squared. And keep in mind, we are multiplying this number by cosine phi prime, integrating over phi prime from 0 minus pi to pi or 0 to 2 pi. So the only term that will contribute will be the term proportional to cosine phi prime. The other ones will just give me 0. I made one mistake though. No, I didn't do a mistake. No, sorry. Now, what I was considering was, you see, I obtained this general expression. I said that for a general point, this is my expression. But shouldn't I have replaced phi prime with phi prime minus phi? I will be rotating my system, let's say, by phi to obtain the vector potential at some point. By the way, I don't like my answer. Hmm? You see, I don't need to shift it. Because you see, I'm integrating over one full period of phi prime. So that is kind of what saves me. Even if I shift phi prime, I can just, using the periodicity of my solution, since I'm covering my full period, well, the period I can just consider from 0 to 2 pi or from phi to phi plus 2 pi. So it doesn't really make any difference. It's not that I don't like. I don't like that the vector potential is in the r hat direction. That is the thing that's kind of buzzing me. Now, let's look at the magnetic field. I mean, we will continue along this line. But now what we had shown is phi a r is in the r hat direction, multiply with some function of r, right? This is the vector potential I have. Now let's calculate the magnetic field, if this is actually the case. Okay, so here I have the expression of the curl in cylindrical coordinates. Let me just curl of A. It never involves the S derivative is equal to 0. Oops. It's a radial function, which depends only on the radial coordinate. If this is the case, then the curl of A is 0. So we did a mistake somewhere. Let's go back. I don't think we have a problem with this final expression of A. Now, because what we had actually done is we had the J integrated over dV. This we can always replace with I integrated over dl for a line charge. This always works. So this is our A. And then this phi hat vector, is this correct? So you see, if we look at it from the top, this is my x, this is my y, this is my r prime vector, this is phi, this is phi hat at the point r prime. So its x component is negative, but it is, no, it's not, it's sine. You see, cosine. Yes, x component is cosine. When phi prime is 0, it is purely in the y direction. Now it's sine. You see, when phi is 0, phi hat is in the y direction. So it should be the coefficient of x hat is sine. The coefficient of y hat is cosine. Is this r prime vector is cosine phi in the x hat plus sine phi in the y hat. And now this r hat prime. R hat prime and phi hat prime, their scalar product should be 0. So it's minus sine phi prime plus cosine phi prime. That's also, I'm sure about that. Now r minus r prime. R is on the yz plane, so the components of r is r in the y hat direction plus z in the z hat direction. X is equal to 0. R prime is, no, this is r prime cosine phi. No, this is r prime cosine phi over here. And sine phi over here. You see, this is my r hat prime. And so let me rewrite over here. Okay, r prime sine squared phi r prime cosine squared phi prime in the x hat. I'm taking the square of the x component. The square of the y component is r minus r prime sine phi squared, sine phi prime squared, plus z squared. Do you agree? The first is the square of the x component of that vector, which is r prime cosine phi prime. The second is the square of the y component, which is r minus r prime sine phi prime squared. And the last one is the square of the z component, that is z squared. Now let me just make the corrections over here. This is cosine squared. This is sine phi prime. This is sine squared phi prime. So this is not cosine phi prime. This is sine of phi prime. Okay. So let's go back. Let's come here. So here we have this. This one is sine of phi prime. So here I have a sine of phi prime. And I'm integrating over phi prime over one full period. Now I cannot use the argument of odd on even functions at this stage, but there's still another argument I can use. You see, look at the cosine phi term. I can just integrate it trivial. It's just you see, if you take the numerator and take its derivative with respect to phi prime, you just get that cosine phi prime. So that the integral of the cosine phi prime term is basically a function of sine of phi prime. The indefinite integral is a function of sine of phi prime. Do you see it? Yes, so let. Or let me take this part. I'm looking at this integral. This integral is nothing but, let me forget these ones also. The integral is nothing but r prime squared plus r squared minus 2r r prime sine phi prime plus z squared to the power 1/2 multiplied by 2 divided by minus 2r r prime. Phi prime from minus pi to phi prime is equal to plus pi. Just take the derivative of that term with respect to phi prime. Well, if you take the derivative, I have a factor of 1/2. That cancels the overall factor 2 I put over there. I have to lower the power by 1 so that 1/2 becomes minus 1/2. That is what I get. And I have the derivative of what is inside that square root. The derivative of what is inside the square root is just minus 2r r prime. That's cancelled by the previous factor, cosine phi prime. That's exactly what I have as an integrand. But you see, sine phi prime, whether I put phi prime is equal to minus pi or pi, is the same thing. It's periodic with period 2 pi. So that integral is 0. Now I like the result. So if you go back, the contribution of the second term is 0, not the first one. And hence the result is, let's say I have the minus sine of phi prime in the x-hat direction. It's the first term that survives. Now it's a minus x-hat direction. Let's look at our problem. Minus x-hat direction is nothing but the phi hat direction. We are on the yz plane. On the yz plane, y positive, minus x-hat prime is into the screen, but phi hat prime is also into the screen. So for an arbitrary point, the only thing I need to do is just replace that x-hat. So you see this is sine phi prime. It's not r hat direction, it's in the phi hat direction. This is the correct result. So let me just erase these, forget about these for the time being. If necessary, we can do it again. So A, as a function of position, is a vector in the phi hat direction, and it only depends on r. AR being that integral over there. Now we can calculate the curl of A. Now the curl of A in cylindrical coordinates, let's see, I have only the phi hat component minus derivative of A. I only have the phi hat component which depends only on Z. Minus derivative of A with respect to, no, on R. No, hold on, is it again 0? R and Z. It also depends on Z. The Z is over there. It's not just R. It just doesn't depend on phi. That is what we expected because of already our system has a rotational symmetry. Okay, now it makes sense. Minus derivative of A with respect to Z in the R hat direction. And plus 1 over R derivative with respect to R of R times A in the Z hat direction. Minus del A over del Z in the r hat plus in the z hat direction, if you just take these derivatives, derivative of a with respect to r plus 1 over r times a in the z direction. Okay, so this is RB. The only thing we need to do is just somehow evaluate this integral as a function of phi. No, and let me just make another correction. This is not cosine, this is sine phi prime. Okay. Well, I will not take the large distance limit. We don't have time. We can continue it on Friday. Okay, so do you have any questions before we continue? Well, it's just algebra mainly. Just calculate the algebra. One thing you have to pay attention to when you are calculating this thing is that always go to the Cartesian coordinates to calculate the components. That is what we had done over here. Yes, at this point, we had already switched to the Cartesian components. And it was kind of nice because the current is in the phi hat direction, and the vector potential is also in the phi hat direction. And then we will look at the, for infinite line, we had already calculated the magnetic field. We can calculate the vector potential for an infinite line. And we will see that the vector potential is also in the direction of that line. Any questions? No. Okay, so see you on Friday.